Have a request for Winter 18, Part 4, Question 1, which will be the question on your test with the most points of any. And they don't take as long as things like nomenclature. So this is where you should start. Strong suggestion. And we are promised on our test that your first step, no matter what mechanism you're looking at, is always going to be the same. And what is that? The pi bond attacks which hydrogen? Which proton? Yes, the strong acid. So whether it's this reaction with this strong acid or the HBr reaction with HBr or the HCl reaction with HCl or the HOTS reaction with HOTS, you're attacking the strong acid. Do not attack water. It will be a disaster. You will lose many, many, many points, both for the mechanism and for the labels. Don't pretend you live in a universe where a pKa 16 reacts before a pKa -5. This is your billions of folds in error when you do that. So you are promised you must do this arrow. Pi attacks H, sigma becomes lone pair on the adjacent atom. All right. Do both copies of the, do each carbocation that's possible. An alkene has 2 carbons. No matter how complicated the molecule looks, there's only 2 cations you can draw. The one on this carbon, which means you put the H down here, or the cation here, which means you put the H up there. I do not need to see your H. I know it's there because you didn't put a plus there. So we're going to draw. I don't like cyclohexane sideways, but you know, I'm doing it. You're going to need both cations, I promise. And I know I need a third cation that's either one of those or a new one, but it has to be one of these. So you're going to need a copy of one of them. And you're asking, which one do I need a copy of? You need a copy of the only one that is a candidate for carbocation rearrangement. What is the criteria for a candidate to be a carbocation that can rearrange? No. It's adjacent to a branched carbon. This cation is adjacent to a branched carbon. This cation is not. This is the one you need 2 copies of. You must draw a second copy. If you try to do 2 things with one molecule, I'm just going to cross off the second thing you did. You're going to get no points for it. You can't do 2 things at once. Molecules can't either. We have a question after I copy the carbocation. Sadly, well, they got drawn so fast, they think they're the same time. And don't worry, I haven't forgot your question. You need 2 copies and we have a question.
So you had a question on the text, which one of these is stronger?
More stable?
More stable, sorry.
Of these 2, the first cation is more stable because it's secondary. And the second one's primary, so it's less stable. And the first one can rearrange to an even better cation.
So that would be major.
Yeah.
Can you repeat that, please?
Oh, the first cation I drew, the first cation I drew secondary. So initially I form more of that. The second cation I drew is primary. I draw less of it. It has less hyperconjugation. And I think I see product number 1 coming from here. And I think I see product 2 coming from here. The O goes where the cation is. Okay, so what puts the O on there? What molecule do you react the cation with to put the O on there? Do not say OSO3H negative. Don't say that. It's not what attacks. You're going to need it later. So I'm drawing it because I'm going to need each one of these later. And I made them every time I made a cation. Don't forget the charge. I see a lot of students forgetting these charges every time a half point off. So if you left the charge off all three of those, -1.5. Every time you do a formal charge error, half point taken. What puts the O on there, ladies and gentlemen? No, protons don't have an O. What molecule has an O that's not the sulfate ion?
Oh, H2O.
Thank you, H2O.
Oh,
H2O. It's going to make the conjugate acid of the product. Don't forget, you need to make the conjugate acid in this reaction. And then take the proton off. Notice my arrows end right at those carbons. They're not ending in outer space. All right. So we got our, I can put the O upstairs here. Water did not miraculously lose an H. The mechanism would have showed that if it did, and it does not. So water still has two H's, and now it's in a family called what? O with a positive charge. What family are we talking? For pKa determination, what family is an O with a positive charge? What's it called? Oxonium. You can take the H off an oxonium because now what kind of an acid is it? Strong. So even a weak base like sulfate ion, hydrogen sulfate, isn't that the weakest base you know? What is its conjugate acid right here? What's its pKa? -5. What's 14 minus -5? 19. 19. That's the highest pKb we can have in this course because it came from the lowest pKa. Think about it.
yeah.
Our weakest base is right here. Please don't be doing things like taking an H off water with this base. It doesn't do it. But you can take H off a strong acid with this base. And let's do that. The base grabs a proton and you made the second product with this. And instead of making a messy page, I'm going to go to number 2 and just label these 1, 2, 3. And I know I can't see 3, but there's a rearrangement for 3. I'll tell you how I know that later. And this next one is going to go to 1. It's going to go to 1. What's going to take the H? Same thing that took it last time. There. Goes to 1. And then I'm going to show you a neat little trick for the third product. Even if you can't do rearrangements, you're stuck. You don't know how to do a rearrangement to save your life. You can still get all but 1 point. What you do is you say, okay, I don't know how this rearrangement stuff works, but I do know that every time I made an alcohol, the O went to the carbon that was a cation to make that happen, right? Why don't you draw the cation like up here this time? The cation you must have before you make that product has to be this one. You must agree. That's the only cation that can make this product. Just like this is the only cation that can make that product, and this is the only cation that can make this product. So you get a point for drawing that, even if you don't know how you made it. And you're going to get a point by putting the O on it the same way you put the O on the other two. What must this molecule react with to put the O on it? We did it twice already. H2O. Somebody's trying to remind me of some important date here. Okay, and that goes to the oxonium. So you're going to get a point for the oxonium still, even if you don't know how the cation happened. Something's got to take its H. What's that something? Same thing every time. Yeah, look, oh, this is going to be the world's biggest mechanism arrow. If you don't like this, you can redraw the sulfate ion closer to your molecule. No objections. And that gives product 3, doesn't it? And you want your 1 point that you're missing? You want it? What moved to get this to have a full octet and be a CH2? I think I just gave you the answer. It's a C with 1 H right now. What moved to make that a CH2 and this a cation?
Proton.
Okay, a hydrogen. Yeah. It's not really a proton. It's taking its electrons with it. Back in the day, they used to call it a hydride shift because it kept its electrons. But you had the right idea. And you've got to take the electrons from that bond and move them next door. And that's going to make, I don't know how to do this nicely without making a huge mess. How about saying it goes to here? So you're going to watch the video to figure out why he drew this way up here. It's because, you know, I was pretending I didn't know how to do a rearrangement and I didn't want to lose more than 1 point. So remember that. That's what I did this morning too. You'll see all of the cations where there was rearrangement. I drew them underneath the products because I just had to copy the skeleton and put the cation where the new group was. You get a point for each cation. And then you get a point for the mechanism step after. So don't stop if you're stuck here is what I'm trying to say. You're going to lose a lot of points. Okay. And then the easy points are the labels. Just remember, where an arrow starts is always a lubnu. Lewis base, synonymous with nucleophile. Yes, ma'am.
So when H2SO4 is regenerated.
Here, here, and here. Yes.
Then it gets from the hydrogen that is when the water.
The oxonium
binds the
hydrogen.
molecule. Yeah, so that's when one of the H's.
The H comes from there and makes this into sulfuric acid. You don't even have to show me. Look, I didn't write sulfuric acid again once, did I?
So we don't have to.
You don't have to. It's a side product. I don't really care about side products unless they're involved in the next step. That's why I drew it here. Otherwise, I would have left that out too, but I have to use it, so I need it.
If we just drew the O, that would be wrong.
The O.
The oxygen. Like, you see how you have the oxygen full carrying the negative sign? If we
Yes.
just do that, that would be wrong.
O without the minus?
SO3H.
Without the SO3H. Well, you're
Just to save like space.
no, you're not. No, you're not using the right O. You've got multiple O's on a page, and you're not telling me which O to use.
Gotcha.
You got to tell me which O to use. All right. Now remember, the start of every arrow makes that molecule that it came from is a lubnu. Period. And we'll do those in purple. That's a lubnu. Just want to go lubnu all over the place and then worry about Habibis later? Let's do that. Every molecule that starts an arrow is a lubnu. I want to put it closer to the molecule. It's this molecule, right? I mean, isn't this pretty fast points? Every time I do the pair, I get a point. We're almost finished after this too. Well, you haven't done any of the ELAs. Did I get all the ones that start arrows?
Yeah.
Yeah, I think I did. And everything they attack is an ELA. Everything that gets attacked is an ELA. It's being attacked by what? Electrons. You must love them if you're going to be attacked by them, right?
That makes it a Lewis acid. Right?
Yeah. You're accepting electron acceptor. Lewis acid. You get them all? For every, oh, I missed one.
Just the one on the top.
The very first, yeah.
Yeah.
And then we'll decide on whether we get BB and BA at the end. I've never done it this way before, but I think I'm liking it as a teaching skill. If your hydrogen's getting attacked, then you're a Bronsted acid. And the thing attacking you by virtue of attacking an H is a Bronsted base. So I'll put those in pink. An H is being attacked. And you're picking up an H there. Don't do it for water. It's not attacking an H, is it? Don't be adding BBs and BAs here. This is a rearrangement. I don't want to hear about stuff. You need two molecules reacting, but this is picking up a proton way over there. And this is providing the proton. This is providing a proton. This is picking up a proton. These are done. These are done. This is a BB. I don't know if I do like this way. It's kind of scattered.
No, that's good. I like it.
If you're liking this way,
Yeah.
it's a new thing, and you should adopt it. If it works for you, that's the only thing. If it works for
The
you.
way you just said it, the arrow points to something, that means it's.
Eli. Yeah, if it points to you, if you're getting an arrow hitting you, you're an Eli.
Yeah.
If you're attacking, you're a Lubnu.
Yeah.
Case closed.
Yeah.
If the thing being attacked has a hydrogen that's getting attacked, it's Bronsted. Remember, never put a Bronsted base with a Lewis acid. You can't be an acid and a base ever. Okay? If there's an A here and you're going to put a Bronsted, it's a Bronsted acid. Yeah.
It's just difficult to understand it with arrows only, like, then you have to remember what you did on this step and who attacked what.
Yeah, you do have to remember. That's the most important part. Once you got the mechanisms down, then the labeling is just reinforcing your understanding of mechanisms. I'm just being a sneaky teacher, trying to reinforce the things you know, make them more solid for you. Okay, so, oh, I missed this entirely. Look at this. Oh, no, I lost a 1.5 points. Oh, no, it's here. Never mind. I'm confusing myself. The labels for this molecule are right here. Okay. Did I get them all? Ilaba, Ilaba for the 3 oxoniums. Good. Lubnu, Habibi for the ones that taking the H off those. Every one of them.
What about
Every one of
the
them?
on the top right?
Ila and Lubnu. This one?
Yeah, no Bronsted afterward.
No Bronsted, or because this is not attacking a proton, is it? It's attacking a carbon. That's not a proton. And then we haven't done our. I think we have to circle major and explain. Maybe circle major and explain. You need to find the best carbocation on the page because the rate determining step is making the carbocation. And it's a tertiary carbocation right here. Your explanation better focus on that guy right there, not on this guy. Every one of these alcohols has roughly the same stability. You start saying one of those is more stable, and I'll just say, no, that's not true. It's the making the rate determining carbocation that's the slow step. This will be the fastest one. And you're going to write it like this, part B. We'll do all of part B in orange. There's your circle. And then you have to talk about this tertiary carbocation forms fastest because it has the most, what's the magic word? Oh, don't say hypo, opposite, hyper conjugation. There we go. That's also part
So if it forms
B.
the fastest, does that make it?
That means over any given interval of time, you made more of it. If you're forming a secondary cation at like 5 cations per second, and you're forming a tertiary at 35 cations per second, in 1 second, which one did you make more of? The tertiary. I don't know if I got the audio on there. There you go. Well, bonus if you could hear what I just said to her. Okay, I think everything's done.
The part C.
Parts, yeah. And after I stop, I'll do a point count for real on this. And I'll fix the point counts because they're not right here. And we're gonna stop.
Can you please ensure you post them like